Okay, so we have been working on various expectation values, and we have been using this wave function. We have evaluated various averages in bits and pieces. Let's try to bring them all together. We had this Gaussian object. I'll just draw the envelope. Okay, so as a function of x, our psi has the form, okay, psi of x at a certain time has the form a e to the minus x over x0 squared, and we also have an I k0 x part to it. Okay, we normalize this so that the integral under the magnitude curve is equal to 1. And when we normalize it, what do we get? We get a is equal to, check my algebra, when I evaluate the integral, I'm going to get pi, okay, square root of pi over the coefficient, so it's going to be 2 over x0 squared, okay, square root, but we really want minus a half power of that, okay. So assuming a is real and positive, this is what we would get. So we would get 2 over pi to power 1/4, 1 over square root of x0. Okay, so with that value of a, the wave function is normalized. Okay. And then we looked at various averages. We looked at the expectation value of x. So that was equal to what? What is the average value? 0, right? It just sits at x equal to 0. We looked at the average value of x squared. What was that? Remember? Well, the average of x squared must have units of distance squared. Okay, so it's going to be x0 squared over 4. And if I now look at what delta x is, so delta x is going to be square root of, okay, x squared average minus x average squared. That's going to be x0 over 2. All right, and then we looked at the expectation value of momentum. Remember, these things are all just simply, if you are looking at some function of x, some average of x to the n, for example, is just psi star x to the n psi dx from minus infinity to infinity. We identified a similar quantity for momentum. So let me write it also as p to the n in some general form. That is going to be, again, minus infinity to infinity, psi star, and in place of the p, we put in an h bar over I del x to the nth power psi dx. Okay, so this object here is now the operator associated with p to the nth power. We looked at what the average value of p was. What did we find?
It was
Okay, it's h bar times k0. Okay, so you see, it's the first time we are seeing this k0 in. Okay, so it's just this wave function, a real function, multiplied by e to the I k0x. That I k0x part always canceled when we were looking at averages of x, okay, because psi comes in with a psi star and the psi, so e to the I k0, e to the minus I k0, they cancel, so the x results are independent of k0, but now that we have evaluated the derivative to find the expectation value of p, that brings down a k0 down, and now we have expectation value of p related to h bar k0. In fact, this is quite a general behavior. You can easily convince yourselves that if the function is only real, if it's not complex, if it's just a real function, then the expectation value of momentum has to be 0, right? Yes?
As for the momentum, we define momentum as the m times the
yes.
mean of x divided by dt, right?
Mm-hmm.
So, if I encountered some problem where I am working, when we try to take try to calculate momentum in other way, I mean taking the derivative, we end up with 0. So 0 doesn't equal to h times k. So how can we reconcile them? I mean.
Okay. The question is, there may be some problem associated with finding the momentum. Most likely, okay, the wave function that you are using is probably something like piecewise linear or something like that. Okay, so whenever you have a wave function which perhaps looks something like this, psi as a function of x, this was also one of your, I think, homework problems or something. So if you have a psi which looks like this, for example, this is not a very physical psi, but any psi should be acceptable. You see, when you evaluate a derivative of this psi, you have these discontinuities and you have to handle them properly. Okay, so you can say, well, the derivative of this function, so let me write e psi dx. So let me just give some numbers. Suppose it has magnitude a and minus a here. You see, this is, the derivative is 0 until the x value reaches there, but then there's a jump, okay, to minus a, which means that you are going to get in the derivative a delta function of magnitude minus a. Okay, so, and then this is going up into 2a, and then going down again at minus a. Most likely, okay, this is one source of mistake, that if you ignore these discontinuities, derivatives of discontinuities have to bring in these delta functions. Okay, so you have to take care of that. But otherwise, the result of an integral, obviously, is something which should be the same no matter how you do it. Okay?
So I think he was asking why can't you find the momentum by taking the derivative of express of x by t.
Okay.
For example, even for this case.
Okay, now, okay, that's actually a good question. Now, when we write down the wave function like this, we are writing it at a certain time. So there's no time dependence in this psi. But this psi will be changing. Okay, that psi will be changing as a function of time. So if you are interested in finding how this psi changes, you have to put this psi in also as a function of time. So suppose you write this thing as this p's here, then you have to write this psi x, say, at time equal to 0. Okay, so this is something at time equal to 0, and if you want to find how the average value of x changes as a function of time, then you have to actually apply Schrödinger's equation. In that case, okay, in fact we did this in class, what happens is that you have these, so let me just write over here, and the general form of that x to the n is going to be something like this. It's going to be psi star of x and t, x to the n, psi x t, okay, dx minus infinity to infinity. So this is the, so x to the n, this is how x to the n changes as a function of time. Now, if you want to find how this changes with respect to time, you see you have these time derivatives, and you have to differentiate with respect to them, and you have to use Schrödinger's equation. Okay, so that's what we did when we were finding this dx dn. So you cannot just take a function form like this and say that this has no time dependence, so the derivative of average value of any of these x's are going to be 0.
That's what I done in homeworks.
Okay, so if you want to, the nice thing about doing it once is that you get these relations which tell you what this x to the n is for a certain value of psi. Okay, but now if you want to know how this changes, then you have to again use the Schrödinger equation. Yes.
Even though it has a time dependence, we still have, for example, the expectation value of x equal to 0. So it needs to be equal to. It doesn't.
Okay, so in this special case, now, of course, you have to be careful about what is going on. This is the average value of the wave function at time equal to 0. But we need to know what is going on when the wave function is developing. So suppose I have a potential. Suppose I have V of x. So suppose I have a potential energy curve which looks something like this. Okay, it may be a parabola or some other type of curve, but it's not constant. Now, suppose I have my initial wave function, the psi at time equal to 0, which looks like that. What would you expect this wave function to do at larger times? Yes.
Maybe oscillate between 2 points.
Yes, well, initially at least, it will start to move towards the right? Because there's this potential energy curve, and the particle is somewhere here. I don't know exactly where, okay, but it has a potential energy somewhere over here, and it will move toward the right. So this wave function, as a function of time, will move towards the right. So it's the average value of x is going to increase, and then, okay, it will oscillate back and forth because it's a nice quantum well, right? So it will do some oscillations there. So we'll actually solve such problems when we get to it. But at this stage, all we know is that the wave function has this form, and we are not given the Hamiltonian, so we don't know the potential energy. But we are not really being asked how that is changing. Now, this part here, which contains e to the I k0x, tells you also the momentum, right, at that instant in time, at time equal to 0. The momentum associated with this wave function. So if I am specifying my particle, I specify it not only in terms of the wave function, the probability density of where to find the wave function, but also it has some initial momentum. Okay, so this is p at time equal to 0, which will be equal to h bar times k0. So that's the initial momentum with which the particle will move. In fact, I expect this momentum to increase also because it's going to be going downhill, right? So its momentum is going to increase also. But those parts, okay, how the momentum changes in time and how the average position changes in time, those things require information about the total energy, the Hamiltonian. So we are at this point looking at the wave function at a certain time and extracting from it where information about where the particle is, information about what the momentum of the particle is. Okay, so that's what we are doing. How that changes with time is a somewhat second step. Okay, is this all clear? All right. Let's just now move on to p squared, the expectation value of p squared, because I want to also find the fluctuation in the momentum as well as position. So that is going to be equal to my integral psi star, let me just write it out, a e to the minus x over x0 squared minus I k0x, because it's a complex conjugate, right? And then I'll have a second derivative, so h bar over I, and del x squared times the wave function again, a e to the minus x over x0 squared plus I k0x. And I integrate this thing from minus infinity to infinity. All right, so now I'm going to get the square of this, which is going to give me, so let me pull out some constants, a star a and a minus h bar squared. Okay. And then I have the second derivative of that function, so we'll have to evaluate some derivatives. Let me write this piece, minus x over x0 squared minus I k0x. Now, two derivatives of this object. So let me just do that algebra over here. Please check my algebra. X over x0 squared plus I k0x. Okay, so the first derivative is going to bring down the derivative of this object, which is going to be minus 2x over x0 squared plus I k0 times the exponential again, minus x over x0 squared plus I k0x. Now I need to evaluate one more derivative. So there will be two places, okay, two types of objects. One, there's an x over here, but there's also an x over there. So I have to differentiate with respect to both of them. So when I differentiate with respect to this one, I get 2 over x0 squared, okay, times all of that stuff, but let me just put that in a bracket. And then derivative with respect to this is going to bring down exactly the same term, so I'm going to write this as minus 2x over x0 squared plus I k0 squared. And then the exponential e to the minus x over x0 squared plus I k0x. All right, let me just simplify this a little bit. So this is going to be minus 2 over x0 squared 4x squared over x0 to the fourth. There will be a cross term minus 2i x k0 over x0 squared, and then the square of this, which is going to be minus k0 squared, right? Is this correct? That's the bracket. All right, so that bracket now goes over here. So let me put that down. Minus 2 over x0 squared. So as I do this, you see, I can just check the units. The exponential by itself is unitless. So I'm evaluating a second derivative, which means I'm going to get everything should be in units of 1 over distance squared, right? So that is okay. This one is also okay, plus 4x squared over x0 to the fourth minus 2i xk0 over x0 squared. Okay, so k has units of 1 over x, yes.
I think 4 times I x k0.
This one, yes, thank you. Very good. Check my algebra. So this is 4. All right, and finally minus k0 squared. Okay, k has units of 1 over distance, so that this is unitless. Yes?
Why does it need to be distance 1 over distance squared?
Because I'm evaluating a second derivative with respect to x, so it's 1 over distance squared, right? All right, and then I have this term here, which conveniently is already there. Okay, and I evaluate just this thing, dx from minus infinity to infinity. But together with these a's, I have a nice normalized exponential. So things which are constants, for example, this term is a constant, doesn't involve any x. This term is a constant. Okay, so that's also nice. So this is going to give me minus h bar squared. This term is just going to give me minus 2 over x0 squared, because it's just my original psi star psi integral, right? And it's normalized. And minus k0 squared. What about the third term? This term here. What does that give me?
0.
0, right? I have an x here, which is an odd function. Okay, rest of the integral is even. And it's really, the x part is expectation value of x, which I know is 0. And very thankfully, it is 0, because if it's finite, it's going to bring in an I, which will give me a result which will say that the momentum is complex, which will be a disaster. Okay, so this term very nicely gives me 0. Now here I have 4 over x0 over 4 times x squared, which will just give me the expectation value of x squared, right? Because it's x squared times psi star psi. So that is something I already know, x0 squared over 4. Okay, so that's it. Okay.
I believe there's a multiplication of a magnitude of a square.
Yes, that's over here. Okay, h bar is over here.
Amplitude of a square, coefficient. A star plus or minus multiplication.
No, okay, because that's involved in the normalization. Okay, that's part of the wave function. So if I just look at these terms, for example, this term here is just psi star then just some constant minus 2 over x0 squared psi integrated. Okay, so A is inside the psi's and it's properly normalized, so I don't have to worry about it. Okay, any questions? Is it clear? If it's not clear, ask questions. This is, okay, relatively simple algebra, but it's very easy to miss signs and factors and such things, and I may have already missed them, okay? This is not guaranteed to be correct, but at present it seems to be correct. Okay, so the 4's cancel, and this x0 squared will cancel 2 factors of the x0 over there. So this is minus 2x0 squared, this is 1x0 squared. So it's going to be minus 1, so long story short, this is going to be h bar squared, okay, 1 over x0 squared plus k0 squared. Okay, so that's what p squared is. Now I want to calculate the fluctuation in p. So average value of p squared minus average value of p squared is going to be equal to this term. So it's going to be h bar squared over x0 squared plus k0 squared h bar squared minus p squared. So it's h bar squared k0 squared. These terms go away. So I'm left with h bar squared over x0 squared. Okay, so that means, so let me just put them, go back here and squeeze them over here. So the average value of p squared is, well, okay, I'll just write the, let's see. P squared minus p squared is going to be h bar squared over x0 squared. So what does that mean? The fluctuation in p is h bar over x0. All right, so this implies that delta p is equal to h bar over x0. So I have some momentum associated with this wave function, but there is some uncertainty in the momentum. It's fluctuating. How much it fluctuates is independent of the momentum itself, but it does depend on how wide the wave function is. Okay? For a narrow wave function, the uncertainty in the momentum will be larger. Okay? For a wave function that's spread out, the uncertainty in the momentum will be less. Is this clear? Yes.
It might be a simple question, but why would we interpret variance as a uncertainty? Yeah.
It's a measure of uncertainty. You can find other measures also, but this is convenient and simple.
Because literally when we convert the mean and variance, we just said that the distance, the summation, this şeyin ortalaması oluyor ya aslında.
English, we are being recorded.
Sorry.
Okay.
The distances of the some points to the mean and the average of them, right? So why we interpreted this as a uncertainty, I couldn't understand that.
Okay, so let's see. I have a probability function which, as a function of x, is something like this, right? So how do I interpret, how do I find the measure? How can I find some value which tells me what the uncertainty in P is. Now, if the function was something like this, okay, this is P of x, this is the probability function, okay, so as a function of x. If I had something like this, I think you'll agree that there is less uncertainty, okay? I'm pretty sure that the object is near x bar.
Okay, I see your point.
Okay, so how wide this is a measure of the uncertainty. So this may have similar x bar, but okay, how wide, how much the function is deviating from that average value is a measure of uncertainty. Okay, you can find other measures, but this is relatively easy because less algebra. Okay, other questions? All right, now one thing that you can notice here is that if I multiply delta p with delta x, I get h bar over 2. Okay, so as the wave function gets narrower and narrower, the position uncertainty decreases, but the momentum uncertainty increases, and vice versa. Now, why is this happening? We are going to take a closer look at this problem as we develop our formalism into somewhat more advanced form. But just qualitatively, if I have something like this, and I want to represent this in terms of waves. Now, remember that if I had a wave in the form e to the I, okay, p over h bar times x minus omega, well, it's energy over h bar times t. Okay, so we said that this was a wave, an electron wave with a certain definite momentum. So if I have a certain momentum, I have a wave with a certain wave function. And this object here, k, which is p over h bar, is 2 pi over lambda. So large momentum means small wavelength. Now, this function does not look like this function or that function. But if I want to get some information about the momentum here, I would like to somehow relate these things to a wave like this. And you can sort of see that if I want to construct this object out of a wave, I would need a pretty short wavelength wave, right? Obviously, these parts I don't want, but to construct this actual major part, I would need a wave with a wavelength comparable to the width of this wave function. Whereas here, I could construct this out of a wave which goes like that. So normally people would say, what difference, what relationship does this wave have with this function apart from having more or less a little same length scale? But now that you are experts in math about how to construct things with waves, you can sort of anticipate what we are going to do, right? How do we construct a general function out of waves?
Fourier transform.
Yes, we are going to use the Fourier transform. So we are going to get to it. But at this point, you can sort of see that the sharper the wave function becomes, you are going to need more and more shorter wavelengths, which will correspond to larger momenta. Okay, but if the wave function is spread out, then I don't need that many, okay, short wavelength waves, and then wavelength will be larger, which will be okay, smaller momenta. So we'll quantify this a little better, but this is where this inverse relationship between the uncertainty in momentum and position is coming from. In fact, this Gaussian, the Gaussian wave function is called the minimum uncertainty wave function. Okay, so that corresponds to delta p. Delta x is equal to h bar over 2. For all other forms, for all other functions, okay, I should say wave functions, I have delta p, delta x is greater than h bar over 2. Okay, so this relation is usually written as delta x, delta p is greater than or equal to h bar over 2. The only time when you have an equality is when you have a Gaussian. Okay, so this Gaussian has some significance in statistics, and it comes up again in quantum mechanics. Very interesting. So this is associated with name of Heisenberg. Okay, it's called the Heisenberg uncertainty principle. Okay, yes.
I may have missed it, but did we ourselves came up with h bar over 2 value in class?
Well, we calculated delta x, we calculated delta p, we just multiply them together.
And
Okay, so delta x was what?
how we are sure that they are the minimum uncertainty wave function?
We are not. I'm just telling you at this stage what you can prove. We'll prove this, okay? We'll come to a point where we are going to actually show that this is the case. Okay? Other questions? Yes.
I can understand that hard relation between the lambda and...
Okay, I sort of gave a hand-waving argument about why that should be so. If you have difficulty understanding that argument, okay, that's justified, just wait until we cover the Fourier transform. In that case, we are going to see the relationship between wavelength and the momentum. Okay, it will be better operative.
Fourier transform, right?
Yes, but you are getting ahead of me, okay? So you have to allow me to teach you some stuff before we get to that. Yeah. Other comments, remarks? Okay, perhaps one small remark. Let me pass this to the back again. You see, we are evaluating the second derivative here, and it involves some amount of algebra. There is a trick which we can use from calculus, which makes these calculations a little bit easier. So let me just mention that. Okay, so this is just some math. Remember that we said p squared is equal to what? Let me pull out the I h bar over I, sorry. Psi star del x squared psi dx. Okay, so whenever in quantum mechanics you have a form like this, I sort of remember discussing this before, but if you have two functions f and then del x g dx, you can always do an integration by parts because these integrals, for the case when these f and g are wave functions or their derivatives or whatever, are 0 at infinity. So if you do an integration by parts, what do you get? You get a minus, okay, g del f dx. So the derivative goes from g to f. Oops, what's this? Okay, so the derivative goes from g to f, and you get a minus sign. So we can do the same thing over here, and we are going to get then this object squared. So it's going to be minus h bar squared, and the derivative will move. One of the derivatives I can move to this psi star. The other one still stays with psi. And the minus sign. So this becomes a plus. That's very nice, because now this is just two terms. One is the complex conjugate of the other, and it gives you h bar squared integral del psi del x magnitude squared dx. Okay, so this is, because it involves just single derivative, it's usually an easier function to evaluate. And you can also explicitly see that this is positive. It has to be positive, right? It's the average value of momentum squared. Momentum squared is always a positive quantity. So if you are finding the average of objects which are all positive, at the end you must end up with a positive quantity. So if you get negative quantities or complex quantities for p squared, that means you have made an error. Okay, that there must be a mistake in the algebra. Yes?
Is the only reason for this uncertainty principle being x to 1 over x, t to 1 over t, a relation like this, or are there other forms of similar uncertainties?
Okay, your friend asks an interesting question. There's some relationship you see between these variables, and if you look over here, the uncertainty in x is related to uncertainty in p, right? So you sort of expect that a similar relation will occur between uncertainty in energy and uncertainty in time. Okay? So that will happen. And similarly, we are going to get uncertainty relations associated with, for example, angular momentum. And angular momentum and angle, okay, rotation angle will have similar structures. And in fact, if you take a graduate course in quantum mechanics, usually the course starts with, okay, relationships like that. So you see, you have taken the freshman classical mechanics course, but in your second year also you took a more formal classical mechanics course where you have this Lagrangian, Hamiltonian, etc., which have entered into the problem. Now, similarly, you are learning the quantum mechanics in one way now. In fact, in the middle of the semester, we'll sort of restart everything, okay? We'll do the quantum mechanics one more time. And if you take the graduate quantum course, it will be still a different starting point, which starts with these relations about how shift in position is associated with conservation of momentum and such things. Okay, so that's you can sort of see that even in classical mechanics, if there is no change in your system with position, what does that mean? That means if there is no change in your potential energy, because that's the only thing that can change with position. If the potential energy is constant, what is conserved? Momentum, right? If potential energy is constant, its derivative is 0, which means there's no force. If there's no force, the momentum cannot change. Now, if there is no change with time, okay, in the system, what is conserved?
Energy.
Okay, well, that's an easy guess now, of course, energy. But similarly, if there's no change in the system with rotation, as I rotate, I see these things, then the angular momentum is conserved. So these conservation laws are associated, okay, with these pairs of variables, and they also keep their significance in quantum mechanics. Other questions? Okay, so we have done one example with some general type of wave function, but you can sort of, I hope, feel the effect of various terms that go into the wave function. If I have a nice real wave function, okay, so if psi is real, then we have seen that the expectation value of momentum is 0. Now, how do I add momentum to this wave function? Well, if I take this object and multiply it by k0x, it just gives it some phase, okay, some oscillation, and that now is associated with, okay, momentum, average momentum not equal to 0. In fact, it will be related to h bar k0. So that's why we got this relationship between the momenta and that phase term. So that will not enter, this will not influence any average value associated with x. Why? Because I always have this psi star psi form, and the psi star psi form then just removes this factor away, and there's no effect of this on any of the x calculations. But it does give you the p. Okay, so if someone gives you a wave function, and now you know how to calculate the x and the p averages, you can calculate lots of things. For example, you can calculate what is the expectation value of energy. Now, the energy, total energy, we call it, we give it the name H. So H is the Hamiltonian, and that is the kinetic energy, P squared over 2m, plus the potential energy, which is a function of position. It contains x's. So the average value of H is 1 over 2m, average value of p squared, which we know how to do very well, plus the average value of v of x. And this is just some function of x. All I need to do is just plug this between psi star and psi and do the integral. Okay, so if it's a harmonic oscillator potential, it's just x squared. Okay? If it's the Coulomb potential, then I have to work in 3 dimensions, but it's 1 over r. But whatever potential I have, I can find the expectation value for any wave function. So you see, these things depend on the wave function that you have. It doesn't mean that you have solved the Schrödinger equation and found the correct wave function that describes this system. Okay, so someone gives you a wave function out of the blue, okay, just like I did it for you. Okay, says consider this wave function. Okay, what average energy does it correspond to for a harmonic oscillator? So what does that mean? I have this system, perhaps a harmonic oscillator system, so that this v of x is just 1/2kx squared. And then someone tells me that suppose you have a wave function like this at a certain point, what is the average energy corresponding to it? Now, this wave function will move around, etc., do lots of things, but for that instant, I can find out what the kinetic energy and the potential energy on the average is. Now, if we are interested in what happens to such quantities when the particle is somehow at rest, we'll see what that means next time, because these quantum particles never want to stay at rest. Why? Because if they are at rest, then we know where they are, and they have infinite momentum, right? So we have to be careful about those things. Okay, unfortunately, we are out of time to make any more jokes, so I'll stop here.
So when we talk about conservation of momentum, let's say,